Hello, everyone, and welcome. Today, we are going to embark on an exciting and detailed journey into the fascinating world of physics, exploring the intricate connection between the oil drop experiment and electrostatics. Let's begin with a simple but illustrative system. Imagine a tiny negatively charged particle suspended in a medium. Naturally, due to its weight, it tends to move downward. However, as it moves, it encounters an upward viscous drag force exerted by the surrounding fluid or gas. This scenario can be likened to a small ball falling through water inside a bottle, which slows down because of the resistance from the liquid. Similarly, a parachutist descending through the air experiences air resistance pushing upward. In both cases, the opposing force is proportional to the particle's velocity and creates a delicate balance with the downward gravitational force. As the particle continues to move, it eventually reaches what is known as a terminal velocity, a constant speed at which acceleration stops. This occurs because the downward gravitational force and the upward drag force become perfectly balanced. The particle no longer accelerates but continues to move steadily, illustrating an elegant equilibrium between these two opposing forces. This concept is fundamental in understanding not only microscopic particles, but also many natural phenomena in fluid dynamics. Now, let's introduce an electric field into the system to see how electrostatics changes everything. Imagine the top of our setup is positively charged, while the bottom is negatively charged. In this scenario, a negatively charged particle experiences an upward electric force because opposite charges attract. This force acts in the direction opposite to gravity, lifting the particle upward. Here's where it gets particularly interesting. The mass of the particle is extremely small, meaning the electric force can easily exceed the gravitational force. As a result, the particle does not simply fall downward. It is lifted upward by the electric field. The viscous drag continues to exert a counterforce, but eventually, a new upward terminal velocity is established. This delicate interplay between gravity, drag, and electric force creates a striking visual of physics in action, showing how tiny forces combine to produce predictable and measurable motion. Now, let's take this concept a step further and imagine designing a practical electrostatic filtration device. In this system, the electric field is intentionally arranged to point from the bottom to the top. The battery's positive terminal is grounded to stabilize the system, while the negative terminal is connected to an insulated chamber. This insulator is cleverly attached to a weight extending from the middle to the bottom of the chamber, ensuring precise positioning and optimal electrical performance. The chamber itself has carefully designed inlet and outlet pipes through which air flows. Dirty air, containing countless microscopic particles, enters through the inlet. When the system is powered, the bottom of the chamber becomes positively charged, while the top becomes negatively charged. The insulator and attached weight acquire charges according to their position, creating a strong and uniform upward electric field. Most of the particles in the dirty air, such as carbon dioxide molecules, soot, dust, and other pollutants, are negatively charged. These particles experience a downward electric force as they interact with the upward electric field, which happens to align with gravity. This results in a combined effect. The gravitational and electric forces work together to accelerate the particles downward, overcoming the opposing viscous drag. Although the viscous drag is still present and acts to slow the particles slightly, it is simply not enough to counteract the combined strength of gravity and the electric force. Consequently, the dirty particles continue to move downward, eventually adhering to the oily collection plate at the bottom of the chamber. Meanwhile, the clean, purified air, now free from these harmful particles, rises and exits harmlessly from the top of the chamber. This system is an elegant and highly effective application of physics. It demonstrates how microscopic principles, such as the motion of charged particles under electric and gravitational forces, can be scaled up to solve large-scale environmental challenges. Electrostatic filters are used worldwide in factories and industrial plants to remove dust and other particles from the air.